Hey y'all, I'm Brandon, and today I'll be telling you about something pretty hot. It is the Exoplanet Wasp-12B. It was discovered by WASP, which is a pair of telescopes that have a bunch of cameras, giving them a massive view of the sky as they scan for stars that periodically dim. This dimming implies that there is a planet covering or transiting in front of it. The planet WASP-12B was discovered in 2008 with a radius of about 1.79 times the mass of Jupiter and a mass of about 1.41 times the mass of Jupiter. The fun thing about it is that it has an orbital period of 1 Earth day, putting it very close to its star. These parameters make it a hot Jupiter since it is about the size of Jupiter and has a very high temperature due to it being close to its star. It's also shaped like an egg. One of the interesting things about WASP-12B is that its orbital period is slowly shrinking at a detectable amount, implying that it is falling closer to its star. This shrinking orbit was first discovered in 2016 by looking at long-time variations in the orbital period from both new light curves and past light curves from other studies. They found that the period decreased at a rate of about 2.5 seconds per year. This non-constant orbital period is thought to be either from orbital decay, precession from planetary tides, or a combination of both. Others continue to observe WASP-12B to better understand its characteristics, such as the study by Wang and others, where they used data from the Transiting Exoplanet Survey satellite, along with older data to reanalyze the transits, secondary eclipses, and phase curves of the planet. The group found that WASP-12B interesting due to its atmospheric mass loss, variation in its dayside atmospheric brightness, and its gradually shrinking orbital period, which has not been observed with any other exoplanet. The authors present a follow-up study of WASP-12B and the use of test light curves to determine its orbital decay, phase curve, and potential atmospheric variability. The authors used TESS observations with data that spans almost 2 years. TESS is a satellite consisting of a camera suite composed of 4 wide field of view optical cameras, giving a total field of view of 24 by 96 degrees. This data came from multiple TESS sectors, or 3-month-long observations. Initially, TESS observed WASP-12B in Sector 20 of its primary mission. Later, TESS observed WASP-12B in Sector 43, 44, and 45 due to the positioning of the fields, giving it 3 months of continuous data. These observations were used to create the light curves for WASP-12B. To find a planet in the transit data, one must look for periodic dips in the received flux. While looking through the data, an observer can make a guess as to when the first transit happens, and then guess the period of the transit. Astronomers also have access to software like Exoplanet, which will do this process for them. To analyze the transits, the authors used 74 full transit events from the test data and selected all data points with a timestamp within 0.1 times the period of the predicted mean transit time. Selecting this many data points from each transit event ensures that there is enough of an outer transit baseline while also minimizing the effect of orbital phase curve variation. The authors then used Exoplanet software pipeline to model the transit light curves. The resulting transit depths have high mutual consistency, showing that they are all like each other. The authors found the orbital period to decrease by about 30 milliseconds per year. The authors compared this to a model that assumed the period is constant. Since the deviation is quadratic, this implies that there is a decrease in period. The inclusion of the new test data improves the precision of this calculation by 30% compared to calculations done by others. The authors then used this orbital decay data to calculate the host star's tidal quality factor Q, which represents the energy in the orbit defined by the amount of energy lost per orbit due to internal friction. The authors find the tidal quality factor to be around 10 to the 5. This value is lower than what is expected for a star like this, implying that the planet is losing more energy compared to other planets. Generally, the theoretical prediction for star tidal quality factor is in the range of 10 to the 7 to 10 to the 10. This can imply that stars similar to WASP-12B with lower tidal quality factors also have shrinking orbits. The authors do not think that there is a satisfactory explanation as to why there is a rapid orbital decay of WASP-12B. The authors bring a strong case about the orbital decay of exoplanets and show that it is something that can happen. At the time of the paper's publication, WASP-12B is the only exoplanet that has a measurable orbital decay. There seems to be a strong consensus that the planet's orbit is in fact decaying and that the data is being measured is not due to a different reason. One potential cause for the appearance of a shrinking orbit is that the system is accelerating towards us. This is thought to be the cause of WASP-4's shrinking transit time measurement, which is a binary system. WASP-4b, another hot Jupiter, has an orbital period that decreases at a rate of 8 milliseconds per year, with the entire system accelerating towards us at a rate of 0.04 meters per second per day, according to RV data, which is radial velocity data. The acceleration comes from the star's orbit around the center of mass, since it is a binary system. This is probably not the cause for WASP-12B's orbital decay, since WASP-12B is not a binary system. But it does show that a shrinking orbital period may not be caused by something as exotic as a planet slowly sinking into its star. There is also a drop-off in the number of planets discovered in the radial velocity method with periods of under 3 days. One potential cause for this is that the planets get too close to their star and they end up being ripped apart by tidal forces. The reason that there aren't very many planets with very small orbital periods could be because of this, and they're just destroyed by their star. As time goes on, I think we will begin to see other planets with orbital decay. The authors talk about other potential candidates that may have an orbital decay, such as TOI 2109b. This planet has a very short orbital period of 0.67 days and a large mass equal to 5 Jupiter masses, making it a very hot Jupiter. As the planet is observed over longer periods of time, we may begin to see tidal decay and shrinking of orbital period.